So this is just a follow-up video to the first video, 1.1 rate of change. So we left off talking about how the average rate of change is just the slope of the secant to the curve. What does that mean? So let's say I have a random parabola, okay? So the average rate of change will be the slope of the secant line. The secant line is just choosing any 2 points, okay? x1, x2, let's call this x1, x2, and 2. And now we're to connect those two dots. That dotted line is our secant line. And the slope of this line gives us the average rate of change. Okay. And then, well, what's the instantaneous rate of change? Well, the instantaneous rate of change is the slope of the line at the instantaneous point, or in other words, at one instant, at one point. Okay, so here's an example once again. And so I try to find 1 point. So let's say I find this point right there. Okay, so I want to find the rate of change at that particular point. Now, typically, where we have rate of change, where we have two clear points, a point at an instant, to find an accurate rate of change at one particular point is hard to find. Think of it this way: if you want to find your rate of change between 1 second and 3 seconds, like in the last video, we have two values to use. But if you wanted to find the rate of change at, say, exactly 2 seconds, unless you stop time, there's no way for you to actually find the rate of change at exactly 2 seconds, at an instant. So the best we can do is approximate it. Now, how do we do that? Well, if we want to find the rate of change at, say, let's make up a number here, say 3, what we're going to do is choose variables that are very close to one another to accurately estimate what the rate of change is at that point. So for example, I can use 3 and 3.001, or I could use 3 and 2.99. So if I wanted to find the rate of change, so let's say, if I were to use 3 and 4, let's say, okay, this line that I'm drawing, this is still a secant line because I have 2 points, okay? Now, if I were to erase that, okay, and say I choose 2 points that are now between, say, 3 and 3.5, okay, that is still a secant line because you've got 2 distinct points, okay, to give us a secant line. So what we want to do is choose 2 points that are very close to one another to the point where 3, and say right beside it, like right there, 3.0001. Now that line that connects those two dots that are very close is a good estimate to the instantaneous rate of change at 3. So this line that I'm about to draw now, this is called a tangent line. It is tangent to the curve at the point 3. So this is the tangent line. Now the slope of this tangent line will give us our instantaneous rate of change, will give us a good approximation of the instantaneous rate of change. So let's see what this looks like in action. So we have a hot tub that holds 2,700 liters of water. When a valve at the bottom of the tub is opened, it takes 3 hours for the water to completely drain. Okay. The volume of water in the tub is modeled by that function. Okay, where V is the volume of the water in the hot tub when the valve is open. Now determine the instantaneous rate of change of the volume of water at 60 minutes. Okay, so let's scroll down a little bit. Okay. Sorry, my computer's freezing. Okay, so now what this means is, so if I look at this function, okay, it is a quadratic function, it's a parabola. So we have 2,700 to start with, okay? and it is saying it 60 minutes, so 60 minutes, so 60 minutes, so 60 minutes, so 60 minutes is about right there. Okay, so this looks at this. So this looks like it's x-intercept. You can see our x-intercept is 180. Okay, which means it takes about 180 minutes or 3 hours to completely drain. Now, in the context of this question, this part of the graph doesn't make any sense. Okay, because this shows that the hot tub is being filled back up, but it only has a capacity of 2,700, so it's just water continuously going in. So in the context of this question, this is irrelevant. Okay, so this section right here, the first half, represents the volume of water in the tub from here to here, and after 180 minutes, the hot tub is drained. Now we want to find the rate of change of the volume of water at exactly 60. Okay, so we want to know, as the tub is emptying at 60 minutes, how fast is it draining? Now, if you think about, just to kind of give you an idea, think about a Coke bottle. That was supposed to be a Coke bottle. I'm clearly not an artist. That is also not a Coke bottle. Cola. Okay, so picture dumping this bottle out. When water's coming out, okay, it's obviously going to go, it's going to drain a little bit slower here because of that, and it'll drain faster the further down we go. Okay, it's the same idea here. It's draining at different rates depending on the size of the hot tub. How do we calculate at exactly 60 seconds? Well, what we do is, well, let's take a look. Okay, so the tangent point P, so it's 60, so we're being told that it's 60 and 1200, which means after an hour there's still 1200 liters left from the 2700. Okay, where did that number come from? All we did was sub in 60 into the equation and it will give us 1200. Okay, now, so at 60 minutes, okay, with a time increment of 5, this just simply means from between 60 and 65 minutes, so a dot right there, so let's say that's 65. Between those two dots, okay, so point 65, at 65 minutes there's this much left, at 60 minutes there's 1200 liters left. So if we found the average rate of change, so this is the average rate of change, not the instantaneous, okay, between 65 and 60 minutes, it is draining at roughly negative 19.6 liters per minute. Okay, but again, that's a secant line between those 2 points. Okay, we want it to be more accurate, so let's decrease the increment to 3 minutes, so which means we're going to look between 60 minutes and 63, and again use the same formula, y2 minus y1 over x2 minus x1, and we find that it's roughly 19.7 liters per minute. Still not quite accurate enough, so we're going to go even closer and choose 60 minutes and 61 minutes. Okay, and we can see that it's roughly negative 19 liters per minute. Okay, so you can kind of see what we're trying to do is decrease the time increment to get it to be as close as possible. Okay, now we can go from 60 to 60.1, okay, which in this case that will give us 1198, so y2 minus y1 divided by 60.1 minus 60. Okay, now let's take out our calculator. So we got 11 minus 1200 over 60.1 minus 60 gives us roughly negative 20 liters per minute. Okay, so let's get even closer. So now I'm going to skip these two because I think you get the idea. Let's decrease the increment to be so small, so we're looking at between 60 and 60.00001 minutes, okay, which I can't even show you on the graph because they're so close. So between 60 minutes and 60.01, so practically touching it. Okay, now you have Let's get rid of the other green dot. So what we're looking at is 60 minutes and 60.01, which is like right beside it. It's practically overlapping. So we're using those two dots. If I try to draw a line now, this secant line is a good approximation to give us a tangent line, because now when you look at it, unless you really zoom in, this looks like a tangent line at 60 minutes. Okay, so using the bottom interval, we're going to go 0.998 minus 1200 over 60.0001 minus 60, and this should give us a number very close to 20, if not 20 on the dot. 0.998 minus 1200 over 60.0001 minus 60 equals negative 20. Okay, if you were to do these two as well, and you can verify it, you'll find a number that's very close, if not exactly, negative 20 liters per minute. So what conclusions can you draw from this table? That in order to find, because what was the original question? The original question was determine the instantaneous rate of change at 60 minutes. So you can see as the intervals got smaller, so this is a good approximation, which means the instantaneous, I'm going to use IROC to represent the instantaneous rate of change at 60 minutes is roughly negative 20 liters per minute. So at 60 minutes, the tub is draining at approximately 20 liters per minute. Approximately. Okay. So, in other words, finding the instantaneous rate of change is the same thing as finding the average rate of change. You're just choosing a very small interval. Okay. So determine the instantaneous rate of change of x equals 2 for the following without graphing. So I'll do, I'll do example B, and again, all these solutions will be posted. Okay. But if we want to find the instantaneous rate of change at exactly 2, at x equals to 2, so I'm going to choose x equals to 2 and x equals to 2 point, I'm going to use 30001, okay, and then fx at 2, so f of 2.001 is, let's find out. Okay, so we got x, oops, so we've got bracket 2 bracket squared, or cubed actually, again I'm just getting it from here, minus 2 times 2 plus 3 is equals to 7. And then 2.001, 7.01. Okay, so there's our y2, y1. So our instantaneous rate of change is 7.01 minus 7 over 2.001 minus 2, which gives us, let's find out, 7 point minus 7 over 2.001 minus 2, 10. So therefore our average rate of change is, there's no units here, so 10 y units per x unit. Okay, and that's how you find the instantaneous rate of change. Okay, it will be the same with example 4. Again, I'll post a solution to this shortly. Okay, any questions? Feel free to send me an email. Take care.